Welcome to Ask and Learn.
So they want us to answer these questions about this poset here. So we're using division or divisibility of on 3, 5, 9, 15, 24, and 45. So something that will help is if we make the Haas diagram for this. So let's go ahead and do that first. So I think it would be easier if we start on the right since we're doing divided by. So we'd have 45. Then 45 doesn't divide anything in this set. 24 doesn't divide anything in this set either, so these would both be on top here. 15 divides 45, so we'd have 15 here. 9 divides 45, and then 5 divides 45, but it also divides 15. So we have that there. And now 3 divides, well, it would divide 9, it would divide 15, it would divide 24, and then it also divides 45. All right, so remember, all these should be directed in this direction here, but when we do the Haas diagram, we assume it's directed upwards. But the other thing about the Haas diagram is if we have one path going from one number to another, we don't need to draw any extra paths to it. So for example, remember we're assuming transitivity in this. So for 5 divides 15, but 15 divides 45. And then we also have 5 divides 45. Well, we don't need that one. Well, 3 divides 9, which divides 45, but we also have 3 dividing 45, so we can go ahead and get rid of that one there. And so then this here would be our diagram, and we just would erase the directions on all these. All right, but I'll just go ahead and leave the arrows because it really won't matter all that much. All right, so we have this though. So this is the Haas diagram. So maximal elements are going to be elements where there is nothing that is above it in the Haas diagram. You can think about it that way. Or in our case, we want elements that do not divide anything else. So in that case, that would be 24 and 45, and then we can just say since these do not divide anything in our set S. All right. Now for minimal elements, so instead of, actually let me go ahead and scoot this over a little because I'll need to move this down as we go. So for the minimal elements now, well, the maximal meant nothing could divide it. So a minimal means that we have it on the opposite side. So it can divide things, but nothing can divide into it. So that would be like the bottom of our chart here, which is going to be 5 and 3. Or so 3 and 5, since 5 divides 15, 3 divides 9. So we just need to show that they divide 1, but nothing divides 3 or 5 in S. Okay. Now we want to see if we have a greatest element. So a greatest element in this case would mean it's at the very top above everything in the Haas diagram. Well, in this case, we're not going to have a greatest element since we have two elements where they don't divide anything. So there are none, or actually for this they just wanted to say is there, so it would be no, and then we could say since 45 and 24 are maximal elements, but 45 does not divide 24, and 24 does not divide 45. All right, and then we'll have a similar rationale for us having no least element here. So this is going to be no, but now it's going to be since we have two minimal elements, 5 and 3, but 5 does not divide 3, and 3 does not divide 5. Okay, so that's why we would have no least element. Now we want the upper bounds of 15, or of 3 and 5. So all this means is what values are going to be above both 3 and 5, or in other words, what numbers can both 3 and 5 divide in this case? Well, let's see. Well, 3 and 5 can both divide 15, so one of the upper bounds is going to be 15. And then 15, since it's divisible by both 5 and 3, that divides 45, which means it's also divided by, will be an upper bound for that. Now notice 3 is not an upper bound, or 9 is not an upper bound, even though 3 can divide into that, since 5 also cannot divide into 9. And then the same reason for 24. 3 can divide 24, but 5 can't, so it wouldn't be an upper bound. So these would be our two upper bounds for it. And we would say since both 3 and 5 divide 15 and 45. All right, now we want the least upper bound of 3 and 5. So for this, when we look at the Haas diagram, all we want is to see which of these upper bounds is lower. So in this case, since 15 can divide 45, that means 15 is smaller in terms of our upper bounds with divisibility than 45 is. So this is going to be 15 since 15 divides 45. Now for our lower bounds of 45, so this is just a way of asking what values in this chart divide both 15 and 45. Well, 15 can divide both 15 and 45. Then 5 can divide both 15 and 45. 3 can divide both 15 and 45. So, and then similar reasons as before for the upper bounds, we wouldn't want 9 to be a lower bound, since even though 9 divides 45, 9 doesn't divide 15. So those are going to be our three lower bounds, and then we can just say since these all divide, so it's important that we say both 15 and 45. And now the greatest lower bound for 1545, so it's between 15.5 and 3. Well, before we were looking from top down, now we're looking from bottom up. Well, in this case, since we want the greatest, we can see that 3 divides 15 and 5 divides 15, but 15 doesn't divide 5 and doesn't divide 3. So that means 15 is going to be our greatest lower bound, since 5 divides 15 and 3 divides 15. So that means 3 and 5 are both going to be smaller than 15. So those would be each of these for this. So again, you could do this without the Haas diagram, but I feel having the Haas diagram really simplifies everything.